So, thank you. I'd like to thank Kostas for an invitation and Winton for hosting this very nice conference. So, this talk is about volatility derivatives and VIX derivatives, so derivatives on the VIX index, specifically in the second part of the talk, and their treatment in a class of stochastic volatility models we have known for some time now, the class of forward variance models, initiated by Dupier maybe in the 90s and then much developed by Bergomi in the early 2000s. And in particular, in an extension of this class of models that we name rough forward variance models that have gained some attention in the last years, and then I'm going to explain what I mean by that. Okay, so so this presentation will really be about applications of these models from the point of view of a bank, of an option desk. And so the mathematical tools you will see will be rather simple, even simpler than the one of Professor Bouchard. And there's a second talk at the end of the day, right, by Antoine Jacquier today on essentially the same topic. But he's suggesting another solution for the same problem. So stay tuned until the end of the day if you want to know everything by then. So, up. So I'm speaking about volatility markets, right? And as you know, so nowadays this is a very rich world where there's a large set of volatility market instruments, by which I mean derivatives that are whose value depends on some notion of volatility of some reference asset S, okay, in the equity world. And so these are instruments that can be used to hedge the risks of an exotic option, okay? And among them, there's, vanilla options, right? Since when we know how to delta hedge vanilla options, we also use them as standalone volatility, simple volatility instruments, okay? And then there's the set of pure volatility products, right? Which are the variance and volatility swaps since the 90s, maybe. And then more recently, this world of derivatives, futures and options on this VIX index, okay? So I'm going to walk you through this class of products sufficiently quick, I hope. And this also allows me to set the notation I'm using. Okay, so quick reminder on variance swaps, okay? What is a variance swap? A variance swap is a swap, right, that allows you to exchange the realized volatility that this asset S will have in the future with some fixed variance, okay? The payoff, so it's a swap between two parts, and the payoff for one of the two parts, let's say the one that has a long position in the var swap, if small t is the date when the two parts enter in the var swap, okay, then the payoff from the point of view of this participant is this one, right? Is the annualized realized variance, okay, which is computed precisely as the sum of increments of log price, okay, over all trading days TI between now and maturity, annualized, so we divide by the time length of the duration of the period in years, minus, this is what I receive, and then minus a certain amount, which is a variance. This is why I call it V for variance, okay, which depends on the maturity T of the product and is fixed today, okay. So this V small t capital T, standard notation. This is current time, and above there, the index capital T is for the maturity of the product, okay. So this V is what we call the fair strike of the variance swap, or sometimes, well, as I call it, the variance swap variance, right? And it is set so that this is a swap, so as usual, it is set, this is set, this constant V, small t capital T is set so that the price to enter this contract for each of the two parties is zero nowadays, right? So the price is zero, the quotation of the var swap is made by the value of this V, okay? So we can go further. From a combination of variance swaps, we can build what we call forward variance swaps, right? Which are, and here the question is, so I maybe try to make a very simple drawing here, but I don't have technical support. Maybe, can I write? Does it work? Okay, very nice. Thank you. So you will see that I used all this time to make this picture. Okay. So nowadays, but so I hope this helps. I hope this helps. Maybe I go further. So we are living here, okay? And the question is, can we build a derivative that depends on the realized variance of this asset over the future interval T1 and T2, okay? And the answer is yes. Why? Because realized variances are additive, right? So take the variance slope over this interval, okay? It will accumulate the increments of square increments of log of S over this time interval. Take the opposite position, a short position in the variance slope over this interval, okay? So we'll have the sum over this interval minus the sum of increments square over this interval. What you're left with is a product that contains, right, the sum of the square of the increments over the remaining period, okay? So you have exactly synthesized, materialized a product that depends, and we keep my picture for a second, that depends on the realized variance here in blue over the annualized realized variance over the future interval T1, T2. And I have to pay something, okay? So I have to pay something, which is this amount here, okay? I receive something for one variance swap. I have to pay something from the other, okay? And so if you make the computation in the end, you will have to pay or receive something, okay? In this case, you will have to pay something, okay? And this something is an amount that I call V, so second notation of my talk, V with 3 indexes, now current dates, and time T1 and time T2, okay? This is exactly what we call forward variance of the asset over the interval T1, T2, okay? It is precisely the price today of the realized variance of the asset over this future interval, okay? So here realized variances that I'm going to forget about in a second, and all these are implied variances, if you want. These are prices, right? These are prices of future variances, okay? And as I said, it is a combination of these indexes V, small t, capital T2, and small t, capital T1, okay? Which is precisely written like that, but it's not so important, okay? So we can do this with combinations of R swaps. So, then this has increased, right, the number of possibilities in this volatility markets, because now these forward variances, okay, these objects here become objects that can be traded, okay, and so that can be injected in a portfolio and it can be used for hedging, possibly, right? What do we mean by that? So quickly, we mean that if at time t prime, and as I promised, the picture is getting more complex, at time t prime. After t, okay, we enter the opposite position in forward variance swap, okay? So you had a contract that gives you the realized variance over T1, T2. Well, enter in the opposite contract that asks you to pay the realized variance over T1, T2, okay? Well, this precisely offsets the realized variance that we had before, okay? So you have a net position where this is away, and you are only left with the difference of these forward variances, right? So if you followed so far, and even if you haven't, what we can do by only playing in positions with these variance swaps is to synthesize a product, a payoff that is precisely the difference between these forward variances, okay? So we can materialize a portfolio, a P&L if you want, that is linear in the variation of this forward variance, okay? This is one of the important elements of this volatility markets because, right, we can't trade the instantaneous variance of an asset, okay? We can't trade the instantaneous variance of SP500 in this moment, but we can trade, its forward variances, okay? Okay, and what is important is that the initial cost to construct this position was 0, right? Because entering in variance swaps has a 0 position, okay? So summing up, we can materialize a linear position on the variation of forward variance at 0 cost today, okay? Then another definition, the last one, I'm done with the picture, thank you. Last definition for my talk. It's the instantaneous forward variance, okay, which is this, again, 2 index object, psi small t capital T, which is exactly what? Which is, well, with analogy of what we do in the world of interest rate, of forward interest rate modeling, okay? It's the de-annualized variance of the variance swap, its derivative with respect to maturity, okay? So that with such a definition, my objects, my traded objects, forward variances and spot forward variances are integrals of this process, okay, with respect to its maturity index capital U over there, okay? So as I said, that's a complete analogy with the definition of instantaneous forward rates and LIBOR forward rates if you're used to interest rate markets, okay? But now the underlying object are forward variances instead of rates, okay? So let me just point out the very simple fact that with all the definitions we have of these objects, if the forward variance over a short future period, capital T plus delta, if delta is small, this, where are we? Here. The value of this integral is essentially, is very close to the integrand computed for U equal capital T, okay? So these two objects are not very far from each other. Okay, good. Then, we go further, right? Because these are products on realized variances, okay? And since the early 2000s, the CBOE, the Board of Option Exchange in Chicago, started to quote directly an implied volatility, essentially, okay? It started to quote, and precisely, so this is the VIX, okay, and I'm going to recall the definition of this VIX object in this slide, started to quote the market price of something else, okay, now, which is the log contract, okay? So take nowadays a contract whose payoff is log, with maturity 30 days, compute its price, gives you a number, and you quote this number, okay? This is the VIX. Okay, so the square root of this number actually is the VIX. Okay, which is what I'm writing here. The market price of this log contract, okay, you see, with maturity T plus delta, well, delta here is 30 days. F is the forward price of S, okay? If there's no interest rates, this is just ST, okay? The market price, okay, as I said, price this object, take the square root, and this gives you a number. Okay, then how does the CBOE do that? Okay, how do you compute the value of this price, the price of this derivative? You can't do it in a way that depends on the model. Okay, you want to do it in a model-free way. We know how to do it, right? With static replication of this European option, which is the log of S. Okay. This is the statistical replication formula of Karen-Madan, typically. This is how we call it in our master courses, at least. And okay, so you can replicate the log payoff with a strip of put and calls, okay? So here, theoretically, at least, with an infinite superposition of put prices and call prices, okay? Observed at the time of your current time for your maturity T plus delta, integrated against a certain weight, okay? Replication formula for the log contract. You have already seen that most likely, okay? And so, of course, this needs to be discretized over available strikes and maturities, okay? This is theoretically an integral. In practice, it will be a portfolio, a combination of call and put prices. This gives me, once again, a number. Square root of this number is the VIX. Is it an implied volatility? Okay, yes, but this is a small additional remark, okay? It is the price, say it is the square root of a price of the log contract. Is it implied volatility? Yes, because the Black-Scholes price of this object, of this derivative in Black-Scholes model is exactly the volatility parameter of your Black-Scholes model, okay? So price this contract in Black-Scholes, you get sigma. So if I say that VIX is the market price of, sorry, there's a square root, right? Okay, now you see the error here. The Black-Scholes price of this is sigma square, okay? If I take a square root as is missing here, sorry for this typo, I take sigma, okay? In any case, you get that VIX is exactly the implied volatility of the log contract, okay? So we have a market where the underlying object is an implied volatility, okay? That has a behavior that we can discuss a long time, okay? So this is a chart, a very simple chart that you have already seen, most likely here and there, okay, about the history of the S&P 500 in blue and the VIX in or orange in a very long time period from before 2000 to 2006 16, something like that, okay? And you can observe this negative leverage, okay? When SP goes down, VIX goes up, okay? So we can discuss a lot about the behavior of this, okay? This is a zoom on how this VIX object can be considered an anticipation of high volatility periods, okay? If you synchronize it with important events, in particular here, this peak was the bankruptcy of Lehman Brothers in 2008, okay? So, okay, this can be used as a volatility forecast object, possibly. I'm not going to discuss about this, okay? What I'm focusing on are derivatives, right, on this VIX object. So we have an object which is already an implied volatility, and there's derivatives on that, right? So as I pointed out, and I'd like to stress, is the fact that the value of this index today does not contain any more information than what is already contained in option prices, right? Give me option prices, this gives me a number, which is the VIX. Now, today, okay, but the value of VIX at a future date capital T is what is essentially the price of the log contract will have at this future date capital T. So this will depend in capital T on the market implied distribution of S over this time interval T plus delta, okay? So if you have derivatives on this object, okay, their prices nowadays will give me some additional information on what the market view on the implied distribution of the asset at time capital T, okay? And so these derivatives are traded, and they include as the essential objects these futures on VIX index, okay? It's exactly as future as you know. Okay, it's a contract that will give you VIX at a certain future date. If you pay against that a certain fixed amount, they call FVIX for future VIX, maturity T times 0. And then we have options on this object, okay? European options, whose payoff is a function psi here of the value that VIX will have at a future date, okay? Okay, so again, a couple of charts to give you a flavor of how this market data looks like, okay? This is an example of VIX future curve yesterday, okay? So there's one maturity per month, May, June, July, etc., okay? And these are the VIX future values, right? Okay, so nowadays, yesterday at least, VIX was at 1560, 15% is the implied volatility of the log contract. An average of implied volatilities of options, 15%, okay? So we are rather calm period in this moment. So calm with respect to beginning of February, where the VIX was up 50 or 60. Okay, and if you want to enter in a future on VIX for the next month, it's exactly 1 month, the maturity. Well, you can, if you go short on the VIX future, for example, you will receive 16 and you will pay the VIX at that moment, okay? So you can gamble on the fact that it won't go up too much, or, okay, if you want to speculate, and otherwise, so each of these objects can be used as a hedging instrument, okay, against volatility, possibly in a portfolio containing exotic options, right? It doesn't always have this shape, okay? It can have a shape completely opposite shape. This is in this famous period, October 2008, just after the Lehman crisis, the Lehman bankruptcy, okay? So the volatility of the VIX, the implied volatility of SP500 was super high, was here around, it's not showing in this graph, unfortunately, okay? And the future curve is like that. What does it mean? It means that here, the market is anticipating the fact that the volatility might go up in the future, okay? In a few months, I ask you to pay 17 if you want me to give you the volatility at that moment, okay? So market is anticipating increasing volatility, and here the market was anticipating a decrease in volatility, okay? Because market knew that the current volatility was super high because the markets were shaken by the crisis, and it was anticipating that it would go down, okay? So again, this is a phenomenology. This is to show you how the market data for this object, for this derivative look like. Okay, these are VIX options. So options on an implied volatility. Okay, this is what we call, or at least Yes, this is why we can call this the smile of volatility, right? This is implied volatility of options over an object that is an implied volatility. It looks like that, okay? It looks like that. It has this typical, this is the value of the future, typical positive skewed shape, okay? So it's different with respect to the smiles of implied volatility that you used to see for equities, okay? And again, we can discuss about the quality, why the shape of the curve is like that, okay? But so in any case, these are the market data you typically have to deal with for one maturity, right? This is the shortest maturity, 1 month, the shortest maturity on November 2017, okay? Options on VIX look like that, okay? Very high implied volatilities. Okay, good. So these are the data we want to deal with, and so we want to build a model to deal with a set possibly of these derivatives. So I'd like to, so I'm introducing these forward variance models, okay, that we are going to discuss and to extend. And so maybe I'll try to give some heuristic view on how we land on the model class that I'm using, okay, with some really heuristic arguments, okay, which go as follow. So consider we are an option desk that, where is the pointer? That is managing an exotic, not even an exotic, a European option on S, okay? We have a certain amount of hedging instruments and we choose to hedge with the assets S itself and a finite set of these forward variances, right? So as I showed you, these forward variances, what I call capital V, can be traded, okay? So officially our portfolio can be built with forward variances, capital V, TI plus 1, okay? These forward variances that can build with variance swaps, okay? It's, okay, I'm considering a portfolio that contains these instantaneous forward variances, psi TI, for a certain set of future dates TI, which is a simplification because I can't trade exactly instantaneous forward variance, okay? I can only trade forward variance, integrated instantaneous forward variance over a small time period, okay? But essentially the treatment will be the same. You can replace the psi TI avec V TI plus delta, okay? The essence of what I'm discussing won't change, okay? So we have an option on S. We want to give a price and a hedging strategy to that, okay? So the price of this option will be a function of our of time and of the current values of our hedging instruments, right? So S and the forward variances, okay? So this function really for the moment is the function that I'm using in my risk management system, okay? Give me the value of S, give me the current values of the forward variances. I run my code and my code tells me that the price is this, okay? A function. And then what happens in between PDs, Monte Carlo, maybe we don't even know. This might be a black box function, okay? So, okay, so what the desk is interested in is to have an analysis of the P&L, of the profit and loss that hedging this option with the model you are choosing or we are suggesting. What was my sentence? Have an analysis of the P&L that you will get, okay? So if you have say a short position in this option, okay? And the P&L of an open position, which means on a position that is naked, not hedged, is the variation of the price of the option, right? You have this option, you are giving it a price with the function P, okay? P, this is delta P, right? P of T plus delta T. S moves from S to S plus delta S. Xi moves from Xi to Xi plus delta Xi minus the value at the previous time. This is a delta P, a variation of price. Minus this is your P&L, right? Because you have a short position, so the minus in front, okay? And now we are really doing computations that a practitioner might do in this case, okay? This is an open position. I want to hedge it, to hedge the risks, the loss related to this position. So I can start adding terms that will eliminate the first derivatives, right? So I add a delta hedge, dP sur ds, and then we can add what we call the Vega hedge in this situation, which is what? Which is a term, a position in my hedging instruments, in forward variance swaps, that will cancel exactly the first derivative of P with respect to my Xi, okay? And this is the second blue term here, okay? I can hedge a hedge that is exactly this, dP sur dx. Each of this is a finite number of variables, huh? Ti, there's only Ti, okay? This should be a Ti, apologies for the second typo, okay? So this is a finite number, this is a vector state variable. Psi Ti for I from 1 to n, okay? So the partial derivative with respect to each of them, okay? Sum over repeated indexes. Okay, and then this is the P&L of my position with delta and vega hedge, okay? And as usual, okay, my delta hedge multiplies the variation of S, okay? And I have to pay something to construct my delta hedge, okay, in time t. So if I have to borrow the value S times my delta at an interest rate R, because I suppose I have a constant interest rate R for borrowing and lending, okay, I will have to pay this at time t plus delta t, okay? So what is important in this equation, maybe, apart from the, okay, fact itself that we can delta hedge, is the fact that here, as I introduced in the slides before, we can, so in order to have this delta hedge with respect to underlying in my portfolio, I need to pay something, okay, to borrow something to buy S, and so I have a debt with the bank. Here, in order to materialize, once again, this position in forward variances, I don't have to pay anything, right? This is what I explained in the beginning, or tried to explain, by saying that forward variances are costless, okay? I don't have to pay anything in order to materialize this term, okay? Which means that there's no additional minus R delta T times Xi term, if you see what I mean. There's no additional term that contains the cost of borrowing the bank account to construct this position, okay? So then we go on in a standard way, okay? Then what we want to do is a rough, in the sense of coarse analysis, and we would develop our P&L with Taylor at order 2 in delta S, another 1 in delta T, okay? So this is really nothing but applying we'll learn how to use this. Applying a Taylor development to this, okay? The first derivatives will cancel, okay? And then I will be left only with the second derivatives, okay? So I will be left, with respect to time, this term that comes from the cost of borrowing, okay? Rs delta T times my delta, and then I will be left with the second derivatives that will contain the variations, right? The variations of S and the variations of the Xi on the market. On the market, S moves. Between T and T per delta T, S moves, Xi moves, okay? And so in my variation of the function P, I will have these realized movements of S and of the Xi, okay? Then, this is the moment when we use our representation of pricing functions, right? We choose the pricing function. We ask that the pricing function in our system satisfies something, right? And so we ask that at time t, our price function satisfies a certain equation, okay, which will lead us to a parabolic PDE, so which is the parabolic PDE in Black-Scholes, if you want, if there's no term containing forward variance and only this constant sigma, and if sigma were constant, okay, I ask P to satisfy a certain equation where these lambdas are some quantities, okay, for the moment completely abstract, and sigma t is some quantity, again, depending on t, completely abstract. But so if P satisfies this equation, then inject in your P&L computation, okay, you will replace this term here, right? This term here is exactly written as a minus the second derivatives of P, okay? And then what we will get, okay, is the usual form of the P&L of a hedged option, okay? Where I'm hedging with what? With a function P that satisfies this, right? So I get the standard gamma or theta gamma, if you want, form of the P&L. So a P&L that depends on the gamma of the option, so the second derivative with respect to S, and the second derivative with respect to all these quantities where you see that Ti became Ui. Apologies for that, okay? I hope this is not misleading, okay? So it contains all the derivatives, the second derivative with respect to all these variables, okay? That multiply what? This is the important terms, right? This is as we are used to, right? This is what we this is the error related to model risk, if you want, okay? This is what we teach in master courses as robustness of Black-Scholes formula, typically, right? We have the gamma of the option that multiplies what? The realized relative movement of S minus this plus the volatility that I'm using in my pricing function. And here I have exactly the same thing. All the realized movements of these forward variances minus this plus the covariances that I'm using for this psi I in my pricing equation, okay? So all in all, not yet, one step more, okay? This is a long discussion, but I hope it will be useful to introduce the model, okay? All in all, can we go further? Can we hedge further? Can we do something more? Can we do something for this term? Yes, okay, we can enter in an additional variance swap with short maturity, with maturity delta t, okay? Why? And this is very coarse again, but these arguments are taken by Bergomi's book, by the way, okay? And why can we offset this term delta S over S square? Well, just because of the form of the payoff of a very short-term variance swap, okay? Just really because this square of log S plus delta S minus log S is actually equal to this, okay? And just because of the behavior of the log function of Taylor development of the log function, this log 1 plus delta S over S is close to delta S over S, square if you put squares, okay? So you can use log contracts to really, as an instrument to hedge variation of delta S square, okay? This is the realized variance of S on a very short time period. You can offset it with a variance swap, okay? And so this means what? That I add this additional hedge instrument in my portfolio. Well, I will eliminate this, and I will have what? I will have, finally, the final form of my PNL, okay? So look at this line, maybe, if you were lost in the previous slides. I will get a final PNL that depends on what? On the strike that I have to pay in this variance swap, okay? Which is, this is a very short maturity variance swap. So its strike is essentially psi small t and small t on top again, also, okay? So current time and maturity, this is a maturity which is very close to t, which we consider approximated by psi small t, okay? So what does it mean at the end, all these steps I followed? It means that, they mean that if I use as a pricing function, a function p that satisfies the equation that I showed you before, where the volatility square of the asset is psi tt, is the forward variance of a very short maturity variance swap, then I eliminate the first piece, okay? So I've tried to nail it down, the control of my PNL of the position, I've tried to nail it down to this last bit, which is, as far as I understand, a reasonable PNL that you can handle, okay? But you have eliminated, so you see it's really simple computation to eliminate all the contributions of the PNL of my hedged position on the option, okay? If I'm using the hedging tools that I allowed myself to use, the underlying and variance swaps, okay? So this leads us to what? This leads us to the model. Because overall, we want our pricing function to satisfy this PD, right? To satisfy this second order parabolic PD, okay? Where, well, we make some choice, some parametric choice of these abstract lambdas, which are now functions, which can be functions of current time, maturity, and the underlying forward variances, okay? Here, as I said, I want the volatility of my asset S in the equation to be psi, apologies, not to be psi square. Well, these slides need to be corrected, to be psi instead of psi square, okay? But so, in the end, we are finally arriving to our model, where if we want our price function to satisfy this PD, then this PD has, the solution of this PD has a representation in terms of expectations, okay, of a Markov process, okay, by Feynman cuts. So we land on a situation where we want our price function to be given by this expectation where the couple S and Psi, so an asset and its instantaneous forward variance, satisfy a certain SDE that is the standard SDE for a stochastic volatility model, okay, with pricing drift RS, and okay, what? Instantaneous volatility of S, which is given by the square root of this instantaneous forward volatility, time t, and maturity, small t as well, okay? And I'm modeling, in this model, I'm modeling what? I'm modeling in a general situation, I'm modeling all these forward variances, okay, for all possible maturities capital T, okay? I want that they satisfy this SDE for all maturities capital T. I want a process that models my instantaneous forward variance up to capital T, okay? So this is the very general form I can ask for my model, okay? And this is the class of forward variance models, okay, that were developed by Bergomi in the early 2000s, and I'm going to extend even more, okay? So this class, for the moment, is very general and still abstract, right? Because it's a typical situation where I'm modeling a curve, okay? Where I'm modeling a curve, okay? Here I have a family of stochastic curves, okay? Parameterized by capital T, okay? So in this model, the price of an option is a function of the underlying, of the value of the underlying, and of this infinite dimensional object, okay, which is forward variance curve, okay, in this setting, which is of course undesirable for practical purposes. So the question is, are there low dimensional families that I can fabricate, okay, that I can consider, okay? So the answer is yes. And, okay, the most important example is what we know by now as Bergomi's model, okay, which was maybe, as far as I understand, there was a first suggestion of this modeling setting by Dupierre in an article, apologies, okay, in an article by 93, which is difficult to find, and, okay, so it's not quoted so often, but, okay, now we want to choose parametric models for this forward variance Psi, right? And so one very simple parametric model would be this one, okay? I ask that each of the instantaneous forward variances is a log normal process, okay? A log normal process with multiplied by a certain kernel, okay? Certain time function that has this form, okay? And all the Bergomi's model relies on the choice of these functions, okay? Which are exponential kernels containing, okay, possibly two parameters, one k and one omega here, okay? So, well, once I give this model, then everything is very simple, right? There's an explicit solution, okay? There's an explicit solution which is a log normal process with this variance, okay? And what? And yeah, the fundamental property is that, okay, because of the very specific form of the choice of this kernel, okay, each of these forward variances, okay, this whole curve, when small t is fixed and capital T is varying, this whole curve can be written as a function of one single Markov process, which is just an Orsten-Uhlenbeck process, okay, which is this Orsten-Uhlenbeck process, okay, just, okay, remark that we have a semi-group property for this phi, okay, which allows me to write that this integral, there's a phi capital T minus small t that gets out, and I have phi capital T minus small t times my process x at time t, okay? But this is an equation that holds for all capital T, okay? So we have a model where my forward variance curve is actually a function, okay? An explicit deterministic function of one single Markov factor, okay? Which for, of course, computational purposes, pricing purposes, whether I want to use Monte Carlo, particularly if I want to use Monte Carlo, is a particular appealing feature, okay? Of course, we are not limited to only one factor, where by one factor I mean the number of Brownian motions here, okay? I can go up to n factors, okay? And this is the Bergomi's model that was published in his series of papers on smile dynamics, okay? That is exactly the same form as before, apart from the fact that I have n kernels, which is the same shape, and n correlated Brownian motions, okay? So I have n phi I, correlation metric rho between these Brownian motions, okay? The situation is the same, okay? Where I have an explicit solution for this, this explicit solution, this is the solution of this linear SD, okay? Where, okay? So now my forward variances are functions of a factor, okay? A Gaussian factor, x small t capital T, okay? Which is again here a function of n correlated Markov processes that are Ornstein-Uhlenbeck processes, okay? Then, the rough models I'm going to talk about. Okay, so there's this rough Bergomi model that was introduced recently, which reads how? Exactly the same form, okay? It's a log normal process, the exponential of some Gaussian factor. This small x, small t, capital T is my Gaussian factor, okay? But the difference being that changing the kernel, we are, also the authors are, changing the kernel that I'm using in this stochastic integral at the exponent, okay? So from an exponential kernel to a negative power kernel, okay? Here, okay, negative power kernel, okay? This gives me what? This gives me another Gaussian process, okay? Take capital T fixed, this is a Gaussian process, no problem, okay? If H is larger than 0, then this is a perfectly L2 deterministic kernel, okay, no problem. And so this is giving me another model, right? Which was introduced by these authors in this pricing with rough volatility paper, okay? So what is less appealing in this model is that we don't have low dimension representation of this curve anymore, okay? We are not able to write these objects as a function of capital T as so this object, apologies, as a function of capital T and one single Markov process, as before, okay? So this is less. This makes the model more complex from a computational point of view, but it has other appealing properties concerning the structure of implied variances and covariances in this model, okay? So why is this model rough? Okay. This model, we call it rough. Why? Because for the moment there's nothing rough here, right? We changed the kernel to this negative power, okay? We understand it when we look at the model, at the consistent model for S. What we call consistent model for S is the stochastic volatility model for the underlying that I introduced with some pain a few minutes ago, okay? Because in this model, what we are using as instantaneous volatility V is what? Is psi small t, right? Is this instantaneous is forward variance when maturity capital T goes to small t. This is well defined in a model, okay? It is well defined, okay? But it is precisely x small t. It is well defined, but it is precisely the exponential of a process that now, when small t is moving here and here, is a process that is what we call a Volterra process, okay? Or Brownian semi-stationary sometimes, okay, but let's stick to Volterra terminology. It's a Volterra process that, as t moves, has trajectories that are less regular than a semi-martingale, right? Less regular than Brownian motion, okay? This has trajectories that are that have a beta Holder modification for beta strictly smaller than h, where h appears there, okay, which is in practical application more close to 0 than 1/2, okay. So we are using a stochastic volatility model as a pricing model where this instantaneous variance has path regularity that is much weaker than usual models based on Brownian diffusion, okay? So why that? By the way, you might ask, okay, well, pricing model with irregular trajectories, why? Because this comes as a counterpart, as a pricing counterpart of a model that has received a lot of attention in the last years. That is the fractional stochastic volatility model of Gatheral, Gesson, and Rosenbaum, who's used as a model for the realized daily volatility of an asset, right? Which is essentially this, okay? Which is the exponential of a fractional Brownian motion, okay? These authors say, let's consider a model of this form as a model of realized volatility. So this is not the same V, if you want, or at least it is V under the historical measure, okay? And it has some appealing properties in reproducing some features of time series, okay? Then take this model, and this is the work of the previous author, okay? Gatheral, Bayer, and Friz, who say, take this model as a model on historical measure, represents the fractional Brownian motion with one of its possible representation in terms of Brownian motion, here the Mandelbrot-Van Ness representation, that represents Brownian motion, fractional Brownian motion as a stochastic integral of precisely these deterministic power kernels with respect to a Brownian motion, okay? And then with a change of measure, heuristically at least, as we are used to doing with stochastic volatility, okay? This makes you land on the previous model, okay? This one as a pricing model for options, okay? Which keeps this rough nature of the volatility, even if this is stochastic volatility under the pricing measure, because it comes from a model that is rough under the historical measure, okay? So, at least I will have done an introduction for your talk, Antoine. So, we can embed the previous models in a more general class, okay? Which is always the same shape, but where now, okay, where we can consider general kernels, okay? We can consider general kernels, so I have 15 minutes, right? Yes, let's say 10. So where I can consider more general kernels, okay, but this is, okay, nothing much. This is to say that you can consider an extended a class that contains kernels, deterministic kernels that depend on two time indexes, okay, that need to be at least at least L2, so that I can define the stochastic integrals, okay? So this is nothing more than, again, embedding the previous models in only one class, okay? Where the choice of the kernel allows you to restore this classical Bergomi's model or this rough Bergomi model, okay? So what I would like to discuss is maybe 2 or 3 points now. The fact that we are considering a model for forward variances, okay, which contain these kernels that can make the process, if I computed this process at time t and for maturity t as well, process with irregular trajectories, which is not a Markov process, okay, but this is a simple but fundamental remark in this setting, is that each of these forward variances for each fixed capital T is itself a martingale, right? This is just as simple as it is, okay? This process that I wrote here for fixed capital T, as small t moves up to capital T, this is a martingale, okay? This is a Markov martingale, okay? So pricing of options, of derivatives on this object, okay, can be done with standard tools. Once I go up to the level of the model for the underlying, then the problems start to appear because I have to use this process at time small t and small t. Okay, so let me, apologies, go on to my interlude, recall the formulas for the forward variances, okay? And recall that in such a model, now we are using this model, either as a model for the underlying and variance swaps, or as a model for the underlying and VIX, okay? And VIX, that I introduced earlier, in this model is what? Is the price of the log contract, okay? But the price of the log contract in a stochastic volatility model is exactly its integrated variance, right? The price of integrated stochastic variance. So VIX in this model is exactly what I've been calling forward variance until now, okay? So variance swaps and VIX in a stochastic volatility model are exactly equivalent, okay? So this formula gives me forward variance or VIX. It's the same thing if I choose to have a stochastic volatility model, okay? So this class has some appealing properties concerning in particular, so this is what I'm pointing out here. term structure of volatilities or volatilities. So I think that in this moment it's too late for you to focus on on an expression that contains too many volatilities. Okay, so let's say that these models have gained attention. These rough models with power kernels have gained attention because of their properties in terms of behavior of the implied volatility of the underlying. This business of the skew of implied volatility underlying that explodes as maturity goes to zero. There's an analogous property, rather appealing, for the volatilities of variance swap volatilities. Okay, in the sense that these, the variance swap variances in this model are stochastic processes that have a volatility. Okay, and the term structure of this volatility of variance swap variance enters into the behavior of the PNL of my option. Okay, and there are typically target behaviors of these implied volatilities of variance swap volatilities that have power behavior. Okay, and I'm taking this again from Bergomi's book. Okay, what I'm showing here is a function of maturity, capital T months, the target behavior that I want to give in my model for the volatility of a very short, so short t, the volatility of the variance swap volatility as a function of capital T. I want this power behavior. The points, the red points are a benchmark, okay? And the lines, the right picture is a zoom of the left picture. The lines are what this Bergomi's model, classical Bergomi's model, is able to do with two factors and different set of parameters, okay? So the result here is that is a result about the implied volatility of the variance swap volatility, okay? The fact that if you accept to call new, no matter the notation, okay? The implied volatility of variance swap volatility as t goes to zero, tends to a certain object that is a function of capital T, okay? It's a function of capital T and depends on the initial variance swap curve, psi zero, and on the kernel capital K. And on the correlation rho you're putting between the different factors, if you want to use several factors, okay? Then if you just choose psi zero, you choose K, okay, in this right-hand side, okay? You have a function of capital T, which in simple situation of these rough models, okay, when you have only one factor and one power kernel here, this right-hand side behaves, this right-hand side as a function of capital T, when this curve psi 0 u is flat, behaves exactly, if you believe me, as a negative power of capital T. T 1/2 minus h, which is, for those of you who know the skew of implied volatility of the underlying, is exactly the same type of behavior, okay? This also holds for the implied volatility of variance swap volatility, okay? Which is our target term structure. Which means what? Which means that the classical Bergomi's model I started with is able to do this with two factors and two different, essentially with a combination of two exponentials that you can stretch to a power. And these rough models are able to do the same thing with only one factor and one parameter h, okay? So you have less parameters for the same thing. Okay, so takeaway message for the end is that if you want now to switch from variance swaps to the VIX market, the class of models that I introduced so far, a few slides earlier, is the class where, is the class where this instantaneous forward variance is what? Is the exponential of a Gaussian process. Whatever kernel I choose, it's the exponential of a Gaussian process, okay? And, okay, so here you have a VIX random variable in your model. It is a superposition of log normal random variables integrated with respect to this maturity parameter U. A superposition of log normal is not log normal, right? But just because of the very fact that VIX is a one month implied volatility, I'm integrating over 1 month, that is 1/12 in years, okay, which is small. And just because this delta is small compared to 1, these log normal processes that I'm integrating are very highly correlated, okay? And so I have a sum of log normals, which is not exactly log normal, but very close to a log normal, okay? Very close to log normal, which means that, well, think of the implied volatility of this random variable. It's not log normal, but it's close to log normal. It will be very flat. It will be very flat. Problems of these models that have been discussed in the literature so far and that I've introduced is that the smile of VIX option is essentially flat, okay? So the question is how to modify the model so to accommodate VIX smiles. And maybe in 2 minutes I will say that in the next slides that you are invited to look at, I suggest a solution, and there's another possible solution, different, completely different, in this recent contribution, and this is what you will see in Antoine Jacquier's talk at the end of the day, okay? My solution is inspired again by the work of Bergomi and is based on the fact that, okay, well, it's a super simple idea. Huh? I mean, it's not nothing nuclear. Instead of having just exponential of Gaussian processes, well, you can ask for more general functions f of your Gaussian factor, okay? And now there's a list of conditions that I essentially can't walk you through, okay? A list of conditions that I want to impose on my function f so that my model for a forward bias defines a martingale, okay? But this is not complicated. I want a martingale here, I want a martingale here, okay? Again, all these processes for fixed t are Ito martingales, so you can apply Ito's formula, you can work out the condition, the PD that this function f has to satisfy if you want to define a martingale, okay? So this is very simple. And, okay, apologies for skipping all this very quickly. You can represent all the functions that you may want to use as expectations by Feynman cuts of their final condition, okay? And so then you can generate families of models, okay? You can generate families of models where these functions f are polynomials, where the function f are convex combination of exponentials, and maybe just to show you a picture of what this gives, apologies again, okay? You see that my managing of time is perfectible, okay? So in the end, we have simple instances of the model that go from, okay, as simple as it is, from one exponential of a Gaussian process to a combination of two exponential of a Gaussian process, okay? So super simple instances at the end, okay, where I'm adding some parameters, okay? Instead of having only one parameter here, I have 1, 2, and 3 parameters, okay? Convex combination here of two exponential with two different parameters omega, which are our vol of variances, okay? And so, a toy example, okay, you go from this picture, where this is the VIX future curve that I showed you on data. This is toy numerical test no market data. And you go from these smiles, okay, to what happens here, as you expect, okay? You go to this situation where the VIX future curve moves a little bit. Now, of course, I'm not claiming that I'm calibrating this to anything. The VIX future curve moves a little bit, and the smiles of the VIX options for different maturities change a lot, okay? And this can be, maybe final chart, okay? This turns out to be because of the data we are calibrating to, because the smile of this VIX options behaves like that. It turns out that this combination of exponentials are particularly pertinent as a model, okay? So what you have here is a calibration to market data for the shortest maturity on this date, okay? VIX future curve, you can always calibrate that perfectly by choosing your curve size 0. And then you have market in red, model in blue. It's super good, okay, even too good. And, okay, and so it turns out to be a pertinent model in terms of calibration power, okay? Then as I try to discuss, we can also look inside the PNL behavior that such a model will give. And I gave you some glance about the structure of term structure of volatilities that come into play there, okay? So I think that I will go to my summary and maybe stop here. Yes, thank you for your attention.
you have any questions?
In the last plot, you have the VIX time structure and the VIX smile for short maturity.
Yes.
0 point. Did you try to do the calibration on several on the whole surface-ish?
Yes.
At the same time?
Yes, yes, and it works just as well, okay? But I have, what I'm using here is a whole term structure of these smile parameters, okay? So, which is what I skipped, maybe. Yeah, exactly. This is what I skipped too fast, okay? Is it, okay, this model here? Yes. Okay, so I'm allowing, because this fits into the framework of, my framework of generating functions f to generate models, I can have this parametric choice with combination of exponential, I can allow my parameters to depend on maturity, okay? To be term structure parameters. So I can fit, okay, term structure parameters on smiles of different maturities, okay? So going back to my picture, up. So I can fit different triple of parameters, gamma, omega 1, omega 2, to each smile, okay? And it will fit essentially just as well, okay? Then I know you have in mind a question, what if I fix, how much do they move? What if I fix, can I do it with only 3 parameters for the whole surface? I haven't really looked at it. They don't move so much, but I haven't looked at the quality with fixed parameters.
Any more questions? Yes, please.
This combination of exponential models is a two-component mixed model, can be regarded as a two-component mixed model. The combination of exponentials in the previous slide can be regarded as a two-component mixed model. So the gamma, in other words, is between 0 and 1. The gamma term. So if you go to the previous slide, you have 2 exponentials.
Yeah.
Yeah, so this is like a two-component mixed model.
So I'm okay, fine. So I'm fine with the component mixture. Okay, I'm fine with calling it mixture. Then what do you have in mind about?
Yeah, so maybe can you think about adding more components? So like a third exponential.
Oh, yeah. Yes, yeah, definitely. This fits into this.
Yeah, this is interesting. I think so because then you can have like a non-parametric framework. You can have as many components as you like, and based on the data, you can determine the number of components.
You can you can
based on the data which you have at hand, you can assume that you can have as many components as you like, and then estimate the maximum number of components based on the data. I think so this would be interesting from a model estimation perspective.
You can maybe you can. Then I'm not sure. Then if the data depends on the data on what you're doing with the data, right? This.
Yeah, but this is a density. This equation there is a density. The second line. The second line.
The second line.
That's a density.
Yes. Yeah.
Yeah. Okay.
A density in the sense of probability measure. Sorry. Okay. Yeah. Sure. Yeah. Okay. Maybe I understand. So maybe a possible answer to your comment, to reply to your comment, is that you can do some non-parametric choices of f. Okay. But the only thing to pay attention to is that you don't have derivatives, okay? You don't have derivatives on psi directly. Here you're modeling an instantaneous object. You only have derivatives over integrals over integrated psi, okay? So reconstructing the implied distribution of psi from data is not necessary, so it's not easy. But what you can do is, what I again skip super quickly, you can go to the modeling of VIX futures directly with the same framework. Okay? And if you model VIX futures directly, you still work martingales under your pricing measure, and here you can precisely do a non-parametric choice of f. Okay.
Any more questions? Okay, let's thank the speaker once again.